Okay, question 7. The diagram below shows the graph of y equals e to the minus x squared. We are told the graph is formed from two convex sections where the gradient is increasing and one concave section where the gradient is decreasing. Part A wants us to find the values of x for which the graph is concave. So we want the area on the graph, or the region on the graph, where the gradient is decreasing. So we know that dy by dx gives us gradient of the second derivative, d squared y by dx squared. That gives us the rate of change of the gradient. So if we want the graph to be concave, so for concave sections, the second derivative, so the rate of change of the gradient, is negative. It's less than 0. Okay, so let's find on the graph roughly where this region is. So it's where the gradient is starting to slow down and then get negative. So we could say roughly it's from about here, because the gradient stops speeding up, starts to mellow out again, and then as soon as it reaches the peak, the gradient is still decreasing. It's now going into a negative gradient. So we could say it's to about there, when the gradient starts to increase again. So, first up then, we need to find the first derivative. So, if y is equal to e to the minus x squared, then by the chain rule, dy by dx is equal to the derivative of minus x squared, which is minus 2x times e to the minus x squared. So that's our first derivative. Now, d squared y by dx squared is a little bit trickier. We need to use the product rule. So, we're going to differentiate minus 2x. So that's going to give us minus 2 times e to the minus x squared. And then for the second part, we're not doing anything to the minus 2x, but we're differentiating e to the minus x squared again. So we're going to get minus 2x times minus 2x e to the minus x squared. Now that is going to give us minus 2 e to the minus x squared add 4x squared e to the minus x squared. So that is our second derivative. Now we know that has to be less than 0. So we have a common factor of e to the minus x squared, so let's divide that away, and we get minus 2 add 4x squared is less than 0. If we divide through by 4, then that's going to give us minus a half add x squared is less than 0. Now if we rewrite that a little bit as x squared minus a half, and then we can think of that as a difference of two squares, so we get x plus root of 1/2, which is root 2 over 2. And then x minus that. So that tells us that the x values at these 2 points are minus root 2 over 2 and positive root 2 over 2. So our final answer, I've run out of room down there, is x is greater than minus root 2 over 2, but less than positive root 2 over 2. Cool. Okay, part B, the finite region bounded by the curve, the x-axis, and the lines x equals 0.1 and x equals 0.5 is shaded. We want to use the trapezium rule with 4 strips, so that means 5 ordinates, to work out an estimate of the integral between 0.1 and 0.5 of e to the minus x squared with respect to x, giving our answer to 4 decimal places. Okay, so we are given the trapezium rule in the formula booklet. Here it is. So the first thing that we're going to work out is h. Now, the distance between 0.1 and 0.5 is 0.4. So h is 0.4 divided by 4. So h is 0.1. Now for our x values, x0 is 0.1, x1 is 0.2, x2 is 0.3, x3 0.4, and x4 is 0.5. So for our y values, y naught is e to the minus 0.1 squared. 0.1 squared is 0.01, so we get e to the minus 0.01. y1 is e to the minus 0.2 squared, which is 0.04. y2 is e to the minus 0.3 squared, so that's minus 0.09. y3 is e to the minus 0.4 squared, so 0.16, and then y to the 4 is equal to e to the minus 0.5 squared, so 0.25. So now that we got all of that, we can say that the integral between 0.1 and 0.5 of e to the minus x squared with respect to x is approximately h over 2, so 0.1 over 2 times, now it's y0 add the last y value, so it's e to the minus 0.01 add e to the minus 0.25 add two lots of the others, so y1 and y2 and y3. So e to the minus 0.04 add e to the minus 0.09 add e to the minus 0.16. Okay, so plonk that all into your calculator and you will get 0.3611. Cool. Okay, part C wants us to explain with reference to our answer in part A why our answer in part B is an underestimate. So, going back then to what we did in part A, we know that the graph is concave between minus root 2 over 2 and root 2 over 2. Now, these are roughly 0.71 and minus 0.71. So the region that we've just played with is completely in an area or region of the curve where the graph is concave. So, what's going to happen is the trapeziums that we have drawn are all going to be just under the curve. So that means there is going to be area between the trapeziums and the curve. So that is area that is not getting counted in our estimate. So what we have found is an underestimate. So you would need to say something along those lines, maybe even back it up with a diagram explaining how the trapeziums are all under the curve, none of them go above, and that is because the curve is concave in the region. Cool. Okay, the final part, so by considering the area of a rectangle and use our answer to part B, we want to prove that the area of the shaded region is 0.4, correct to 1 decimal place. So, we've just said that what we did in part B was an underestimate. If we go back and instead use a rectangle with the height of the leftmost point on the curve in this region, then what we're going to end up with is an overestimate. So what we've got then is a rectangle with a height of e to the minus 0.01 and a width of 0.4. So the area is 0.4 e to the minus 0.01. Which, if we go to 3 or even 4 decimal places, gives us 0.3960. So we don't really need the 0. So in part B, we worked out an underestimate, which was 0.3611. Now we know that was an underestimate. And what we've just worked out here is an overestimate. So 0.396. Now 0.3611 and 0.396 do round to 0.4 to 1 decimal place. So because our under and over estimates round to the same thing, we've done it. Cool.